Hello everyone, good afternoon to all of you. Welcome back to the next video lecture. And this video lecture is actually comprised of the hydrides of alkaline earth metals. Why actually I am interested the hydrides of alkaline earth metals because of the diverse chemistry it involves. As in the previous lecture, you have studied that all alkaline earth metal, so they exist in their +2 oxidation state. +2 oxidation state, right? So, and they forms ionic compounds. So, because of the high charge density and uh, large electronegativity difference between the cation and anions. So, here a special class of actually compounds, that is metal hydrides. So, metal hydrides actually hydride means, so there is H minus, so it contains 2 electron in the valence shell, so that is 1s2. The electronic configuration of this species is similar to helium, right? So, because of this negative charge, this hydride is actually highly reactive and act as a reducing agent. So, once these metals combine with hydrogen gas to form metal hydrides. In contrast to these metals, beryllium does not react directly with hydrogen because beryllium contains a passivation layer of its oxide on the surface. So, it is not reactive and are not able to react with hydrogen gas directly. But rest of the other metals like magnesium, calcium, strontium and barium, they are highly prone to react with hydrogen gas to form magnesium hydride, calcium hydride, strontium hydride and barium hydride. So, all these hydrides contains such type of structure, that is actually metal exist in +2 oxidation state. But beryllium does not react directly with hydrogen gas at room temperature. So, it requires another process or another route to form beryllium hydrides. So, here we have extracted a reactions from the reference, that is beryllium chloride, right? So, this is your beryllium halide actually. Once react with lithium aluminum hydride, this lithium aluminum hydride is reducing agent, right? Reducing agent. What happens actually, once react this lithium aluminum hydride with this beryllium chloride, it forms beryllium hydride, that is BeH2. In both cases, beryllium exists is their +2 oxidation state, right? So, this is because this is reducing, so it is oxidized in that particular reactions. So, this is the product AlCl3. So, this is reduced. This reactions is reduced. And similarly, this beryllium hydride can be obtained through the reaction of lithium borohydride. Once this beryllium chloride react with lithium borohydride, so this form beryllium B2S6 type of compound by additional product, that is lithium chloride. Now, this beryllium BeB2S6, so that react with a sealed tube containing triphenylphosphine. So if this is heated, then the reaction looks like that. Beryllium hydride BeH2 forms, and as a minor product, so that is PH3 PbS3. So but rest of the metals like calcium, strontium, barium, they directly react with hydrogen, so that form corresponding hydrides. And these hydrides are actually reactive and undergo hydrolysis with water. So once a calcium hydride, or simply you can say any alkaline earth metal hydrides, react with H2O. So this produce calcium hydroxide, and 2H2 hydrogen gas is released. So this water is reduced as a hydrogen gas. So this is your reduction. So calcium hydride acts as a reducing agent, and that reduce the water into hydrogen gas, and this is actually hydrolysis reactions. So where water actually react with that particular species. So this type of hydrides actually act as a hydrogen energy storage, because once they are heated, suppose we have another that is actually magnesium hydride, right? Once this is heated at 250 degrees centigrade, then this produce magnesium solid, and H2 gas is released in the atmosphere. So this hydrogen gas is produced through the heating phenomena. You can simply say these hydrides are actually hydrogen energy storage, right? So this is the implications of the hydrides in a research and innovation technologies. So that is why alkaline earth metals hydrides are important, because of small size of beryllium and magnesium, right? And it has it is actually they are highly charged, right? So they form covalent ionic compounds, but rest of other metal ions form actually ionic compounds like calcium, strontium, barium hydrides, CaH2, SrH2, BaH2. So all these species are ionic. And has a linear structures. So what is the structure of actually beryllium hydrides? In case of beryllium hydride BeH2, so beryllium exists in +2 oxidation state in this particular species. So what is the electronic configuration of neutral beryllium? That is, 1s2, 2s2, and 2p is 0, right? So this is actually your electronic configuration. 2s2, 2p is 0. Here no unpaired electrons are present in the neutral beryllium atom, so it is actually uh, here you can't expect any bond formations either, and that is uh, any covalent bond formations. So the covalent bond formation only is possible if this valence electron is excited to the 2p orbitals. So in these orbitals, so now in the excited state, it forms like that. So this single electron contains, and this also contains single electron, and these two orbitals remain vacant. So here the probability of formation of two covalent bonds uh, because of the presence of two unpaired electrons, and that can share with two hydrogen atoms. So beryllium can form two bond, that is two covalent bond. So because of two unpaired electron in excited state. So here only 4 electron in valence shell, right? Valence shell. So this is not the criteria of the completion of the octet rule, and it has two vacant orbitals. So you can say that this compound, any beryllium hydrides, are electron deficient, right? So because of the presence of these two vacant orbitals, so beryllium hydride is electron deficient. Electron deficient, right? So what is the probability of beryllium 2 plus? So 2 electron is completely removed. So it has actually balanced shell configuration, that is 1s2, 2s0 and 2p0, right? Or not, it is actually 2 electrons completely removed. So what is actually happens? So this two s and 2p, here 4 orbitals, right? 4 orbitals are vacant. So they can accommodate a pair of electrons from Lewis bases. So in this case, beryllium 2 plus act as Lewis acid, right? And they can react with Lewis base to form coordinate bonds actually. So it can form 1, 2, 3, 4, 4 coordinate bonds in this case. 4 coordinate bonds. Suppose we have a ligand that is F minus, so which is a Lewis base. So beryllium F2, so that is beryllium fluoride is unsaturated, and it further react with another F2 molecule, then it forms BFBE 4, right? So overall 2 negative charge. So in this way beryllium attains 4 bond, right? So this is your 4 bond. Now it has complete octet, and it means there is 4 coordinate bond, 4 coordinate bond. So there may be possibility of formation of 2 bonds or 4 bonds with beryllium depending on the nature of the bonds and compound in the physical form, right? So what happens in case of beryllium hydride? In the gaseous phase, this exists as such type of structure. So it contains linear structure, right? But this linear structure is actually polymerized because of the electron deficient nature. So it forms a bridge like structure. So because of the electron deficient nature in beryllium hydride, so they dimerized, trimerized, polymerized through the clustering process to form a linear extended polymeric chain. And now here each beryllium, you can see each beryllium has 4 bond. Now it seems it completely follows the octet rule, and this polymeric chain actually this is BeH2 का whole n exists in the polymer form, and it has a 3D network structure, 3D structure, right? So it contains beryllium, hydrogen, beryllium, right? So in the above of the plane and in the below there is a beryllium, hydrogen, beryllium bond. So this is one type of, and this is another type. So it has 2 beryllium, hydrogen, beryllium bond, right? One beryllium, hydrogen, beryllium bridge is present in the above of the plane of the paper, and second one present in below of the plane of the paper, right? But hydrogen has only one valence electron, right? And beryllium has 2 valence electron. So one electron of this hydrogen and one electron of this hydrogen, that forms covalent bond with this beryllium, right? And rest of the 2 vacant orbitals giving rise to electron deficiency will attract another beryllium hydrides, right? So one BeH2 unit will be attracted towards another BeH2 to form a cluster. So this contains only, here already 2 electrons are occupied in this case. So there is no further electrons, only 2 orbitals are vacant in this beryllium. So 2 electrons in this bond, 2 electrons, and in this bond also 2 electrons. So these 2 electrons will saturate this beryllium, this hydrogen, and this beryllium. And similarly in the below, this beryllium will be saturated by this 2 electron, this hydrogen will be saturated by 2 electron, and this beryllium also saturated by 2 electron. So overall here two beryllium hydrogen beryllium bridge exist, where they are called three centered two electron bond. Three center means beryllium, hydrogen, and beryllium. But in this bond, there only two electrons. So, because of the formation of the covalent bond of beryllium and hydrogen, this two electron will uh, stabilize to all the atoms present in this bridge, beryllium, hydrogen, and beryllium. Similarly, below the plane, these two electrons will stabilize beryllium, hydrogen, and beryllium, all these centers. So, they are actually coming because of the electron deficiency and because of the availability of the vacant orbitals in the valence shell. So, once vacant orbital they overlap with similar compounds to form a cluster, then the structural phenomena looks like that. So, such type of polymeric linear chain actually exist in gaseous phase, not gaseous phase, sorry. So, this exists in solid phase. In the gaseous phase, linear molecule exists BeH2 as a linear form, but in the solid state it exists as a polymeric chain. And such type of beryllium hydrogen beryllium bonds are actually called banana bond. So, this is banana bond. So, beryllium hydride in the polymeric form actually create two banana bond, one above the plane and another below the plane. So, in this way bonding behavior is different to that of the linear structure, and each beryllium is actually possess 4 bonds in the polymeric form, whereas in the solid there is only 2 bonds. So, this is in gaseous state, and because of 2 bonds here beryllium has 4 valence electrons, and in this case beryllium completely satisfied the octet rule, it has 8 valence electron. So, polymeric structure is more stable compared to the linear structure, and then linear structure polymerize itself or uh, catenating to each other to form a polymeric clusters structure. So, that will be highly fascinating, and all the hydrides actually not attains such type of structure. From moving top to bottom, some strontium, calcium, and barium hydrides are ionic in natures. It means they contains M2 plus and H2 minus. So, because of the lattice energy, the ionic compound exists in the nature. So, only beryllium and magnesium, because of the high charge density and small size, they actually form covalent compounds as per the polarization effect and Fajan's, that is Fajan's rule. So, this is due to the actually polarization of the hydride ions with beryllium ions. So, this covalency occurs. So, you can't say beryllium hydride or magnesium hydride is completely ionic, rather it contains covalent bond. So, this is the actually importance or fascinating chemistry involved in the hydrides, right. So, all hydrides are actually important and they are reducing agent for the various chemical reactions occurring in the organic reactions as well as in the inorganic reactions. So, that is that point of view, this topic is actually fascinating and interesting in the chemistry. So, I think this is enough for today. So thank you for listening and watching the video lecture. I think if this video lecture looks good and energetic for your brain, so kindly don't forget to like and share and comment of this particular video. Thank you.